So today's lesson is honestly probably the most kind of difficult, challenging, thinking-wise lesson in all of AP Calculus, and it's something that if you ask someone who's taken AP Calculus, one of the things that they'll tell you is like the hardest was related rates. So it's something that we really need to focus on today. So, anyways, the questions kind of relate a lot to implicit differentiation, but we're taking the derivatives with respect to time, and that's important. So anytime at all that we see the word rate, we want to associate the word rate with time. So instead of so far, almost every derivative we've ever done has been d dx. Now we're going to be doing d dt. So we're still taking the derivative the exact same way, but it's just with respect to time instead. And so what that means is anything that's not time is going to get that implicit derivative that we did yesterday, how we did the dy dx. We're going to do d whatever variable dt. So that's kind of an important concept. So if we were going to take the derivative with respect to time, right, a rate of the area equals 4 pi r squared, that's the formula for the area of a circle. And kind of what we're going to do is we're going to say, okay, we want to do d dt to both sides. So the derivative of a, that's a variable, is just 1, but it's going to become 1 times dA dt. And the reason we're going to do dA dt is because the a and the t, those don't match up. So if they don't match up, you always do that implicit equals. Now, 4 pi is just a constant. It's the same as just having like 12 point something, right? So the 4 pi is a constant. It's going to stay the same. The derivative of r squared, we're going to bring the square down. So we're going to get 8 pi r. But then, because r is different than t, we need to multiply by dr dt, that implicit derivative. And so this would be our equation. So state what this equation means. So what this means, or state what each rate means, what each rate means. So dA dt, that's going to be essentially the rate at which the area is changing, per time. And dr dt will be the same thing. It's going to be the rate at which the radius is changing. All right. So next up, we have volume of a sphere. We're going to do the same thing. So we're going to take the derivative with respect to time. Derivative with respect to time. And I like to write these in. It helps me. So the derivative of v is 1 dv dt. If we don't want to write the 1, we don't have to. So dv dt. When we do r cubed, the 3 comes down, and it's going to, 4/3 times 3 is just going to become 4 pi r squared. And then times the dr dt, right? Because r and t are different variables. So dv dt, that's going to represent the rate at which our volume is changing. And I'm not going to rewrite dr dt because we've already established that's the rate that the radius is changing. Now, something pretty neat about circles, honestly, is this is kind of just a fun thing. You don't have to actually realize this, but when we take the derivative of volume, 4 pi r squared, that was the formula for the area. So now you're still multiplying by dr dt, but it's just kind of interesting that the way that the volume changes for a sphere is dependent on its surface area. So we'll see that even with the way that circumference and area are related as well. If you take the area of pi r squared, you're going to get 2 pi r, right? The area, when you derive it, you're going to get the circumference. So it's kind of interesting. Okay, next up, we have a equals the square root of c squared minus b squared. This comes from the Pythagorean theorem, right? A, b, and c. A squared plus b squared equals c squared. If you isolate for a, you're going to get this formula. But they're telling us that c in this case is a constant. So maybe it's a ladder that's falling, right? Like c is a ladder and the ladder can't change at all. Or some instance where that c is a constant. And so that's important. So um, we take the derivative with respect to both sides. The derivative of the left, the derivative of a is going to be 1 dA dt. And on the right side, we have a square root, so we're going to have chain rule. So the outside is the square root, so 1 over 2 square root of, kind of like our box, right? We're going to do like a box there for chain rule. So 1 over 2 square root of c squared minus b squared. But then we have to chain it times, I'm going to put this in parentheses. Now, the derivative of c squared, remember c we said is a constant. So, put in 3 if you want to, or a number. Like the derivative of 3 squared would be the derivative of 9, which is 0. So it just goes away. Minus, now the derivative of b squared is 2b, but then we need to do times db dt. So every single time with these rates, when we're doing d dt, when we take the derivative of any variable, we always have to multiply by d, the variable dt. So if we wanted to simplify this, right, dA dt equals, we can move this to the numerator. I'm going to cross cancel out my 2's. So negative dB dt divided by the square root of c squared minus b squared. Now, I know technically we kind of have negative b dB dt, negative b dB dt. I forgot that b there. So I know technically we have a fraction inside of a fraction. Don't think of it that way. dB dt is a rate. So it's not really a fraction. It's representing the rate that side b changes. Okay. Next up, we have v equals pi r squared h, where they're telling us that r is a constant. So we have a volume of a cylinder. And so, kind of what this means, right, is we have some volume of a cylinder. And if r is a constant, then maybe, we're changing the height of this. We're making it, we're kind of stretching it. Or maybe even we have water in there and we're adding water. And so the level, maybe we're just measuring the level of the water. And so the height of that water is, getting bigger as it changes. So the volume's going to change, the height's going to change, but the radius is not changing. That's what they're telling us. And so that's neat because we don't have to do product rule here. We literally think of r squared as just a constant, as if it was 3, it just stays. So when we do ddt, right, we want to kind of think of that pi r squared as a constant. If it was 4, what would be the derivative of 4h? It would just be 4. So the derivative of pi r squared h is just the pi r squared part. It stays. So the derivative of v is 1 dv dt. Now remember I said that pi r squared is going to just hang out. It's a coefficient. So what's the derivative of h? It would be 1, but times dh dt. We need to do that dh dt part. Right? So that's the implicit part. So I'm not going to write these because this video is going to be long, but if we were to define these, dv dt is representing the change, the rate that the volume is changing, and dh dt is representing the rate that the height is changing. Okay. Next up, we have a triangle where they've given us 15. Now, 15 is a number, so it's a constant. And they want us to derive this equation, cosine of theta equals x divided by 15. And so the derivative of cosine of theta is negative sine of theta, but then we have a variable, so times d theta dt. And equals, now for x over 15, I like to kind of write this as 1/15 x. It makes it easier on me. Like the derivative of 15x would just be 15. So the derivative of 1/15 x is just 1/15. But because of that d dt, even though it's x, right? With implicit, we didn't do it for x, but that was because we were doing ddx. Now we're not doing ddx, we're doing ddt. And so x is a different variable than our t. So we're going to need to do times dx dt. And so there's our equation. Now, what does d theta dt represent? That's saying how is the rate at which theta is changing, our angle is changing. So maybe we have this triangle and we're changing the angle, right? The angle's getting bigger or smaller. And as that angle gets bigger, if the 15 is going to remain there, then the x, that length, is also going to need to get bigger to maintain the 15. So, or it might even get smaller actually as it gets bigger. So Then we have volume of a cone. Now this time they did not tell us that R was constant, right? In question 4, we knew R was constant, and so we left it. But in question 6, they're not telling us that it's a constant. So we have 3 variables. We have V as a variable, then we have R as a variable, and H as a variable. So this one is going to be product rule because we have 2 variables on the left side. So when we do d dt on the left side and then d dt on the right side, so on the left side, the derivative of V is 1 dv dt. And then on the right side, we're going to have to do product rule. So first, I'm going to take the derivative of R squared. That's going to give me 2/3 pi times R, and then times dr dt, because I did the derivative of an R. And then I leave the second term, the h, alone. Then plus, now I'm going to leave the first side alone, 1/3 pi r squared. We're going to just leave that alone. And times the derivative of h would be 1 dh dt. I'm not going to write in the 1, but it's 1 dh dt. And so that's our equation. You could kind of drop the parentheses and maybe rewrite it as dv dt equals 2/3 pi r h dr dt. I usually write the rates last, so I just move the h kind of in front, and then plus 1/3 pi r squared dh dt. And if you really wanted to get fancy, you could factor out like a 1/3 pi r, but I'm not going to. So dv dt would be how is the volume of our cone changing, dr dt would be how is its radius changing, and dh dt would be how is its height changing. And if we kind of go back to that example I was given of, like, say, filling up a water, right, if we had like the water level right here, we'd see that if we increase the water level and we go up to here, now we're going to have a different radius, right, because the radius would be, bigger than it was over here. So the radius is changing as the height changes. They both change, and that would cause the volume to change. Whereas when we were filling up a cylinder, because the way a cylinder kind of looks, when we fill up a cylinder, the radius, oops, messed up that picture, the radius would not be changing. So if the water level's down here, right, as we increase the water level, the radius is going to stay the same. So that's why we were able to, in question 4, why we were able to say that, hey, that radius will be constant, and so it was a much easier derivative. So in this case, the only thing that would be changing would be the heights. But still, as the heights change, the volume will change. So kind of looking at these, a lot of them time they're going to be word problems. And so we really have to just kind of decipher and be careful. And the first step is always going to be to identify our variables. So I want to kind of jump down here and look at that. First step is always going to be to identify our variables. So that's what I'm going to do as I read through this. So air is leaking out of an inflated balloon in the shape of a sphere at a rate of 230 pi cubic centimeters per minute. Now I want to talk about this per minute. Okay, and you can kind of just add this on the side of your notes. Is right. All of these rates, remember how we said we're ddt? Well, the dt is going to give us a per in our units. So that ddt portion is going to basically tell us that we're going to have per some unit of time. And so whenever we see that per minute, we immediately know that that's not a volume or a radius. We know it's a dv dt or a dr dt or something like that. And really going through on those units, the other thing that we need to know is that basically if we have our units, maybe it's meters, maybe it's centimeters, but whatever. I'm going to put an m in here for meters, but you could put whatever. If we just have it to the first power, that could be a height, it could be a radius, it could be a length, but it's basically some kind of a distance, right? It's some sort of a distance. Then when we see our units squared, that's always an area, or if it's a 3D shape, then it'll be a surface area. But it's basically an area. And then when we have our units cubed, that's always going to be a volume. And so this is really important to memorize. You should have kind of been exposed to this in some classes, whether it be physics or math or even like 8th grade science, or if you took engineering, possibly freshman year of engineering. But that's something that we need to really be careful about with those units. And so squared would also be, they could say square units, and cube could be cubed units or cubic units. But that's something to watch out for. So here, when we're reading about this 230 pi, some key things to look at will be, well, first of all, they told us it was a rate. So they literally told us. But then also the per time, both of those two things, per minute, that's going to tell me that we have a rate. And what's the cubic part doing? The cubic part is telling me that it's the rate of a volume. So what this is going to tell me was that dV dt, the rate of the volume, is equal to 230 pi. Okay. And then if we want to add in the units would be, right, centimeters cubed per, centimeters cubed per minute. Okay. And then it says at the instant. So just at that one moment in time, when the radius, so they gave us that it was the radius, is 4 centimeters. Now notice that there's no per time. So they're just giving us the value of the radius. They're not telling us that the radius is changing yet. It is going to be changing, but they're just saying at that moment when r is equal to 4 centimeters. Then they're asking us what is the rate of change of the radius. So that's going to be what they're asking us about. And that word rate of change of the radius, they're basically saying they want us to solve for dr dt. That's what they're asking us to solve for, is solve for dr dt. So identify which, if any, of the variables in this problem are constant. That's something very important to do, is are any of these variables constant, not changing? And they'll tell you that, you'll look for that. And in the problem, they'll say, the radius or the height or whatever, they'll say is a constant a lot of the times. Or you can do it based on the shape, right? Like we talked about this cylinder having a constant radius. Well, if we were thinking about a balloon inflating or deflating, and in this case, air's leaking, so it's deflating, then we can basically say that there are no constants. Now, I do want to add one more thing, is I actually did make a mistake in number 1, and we always want to be thinking about the signs of these. So if air is leaking out, then that means that this rate over here is going to have a negative. So that's important to think about, because the volume is not getting bigger, it's actually getting smaller. So that's really important to think about. So the dV dt would be negative 230 pi as it's getting smaller, right? If they said you're blowing up a balloon, then it would be positive. Identify the rates that are given and the rate that you wish to find. Okay, so they gave us dV dt, we already know that. So they gave us dV dt equals negative 230 pi centimeters cubed per minute. And we want to find dr dt. And just as you don't have to, you're not going to make a table like this every time you do this. This is just for us to kind of talk through it. So let's kind of think about what units should dr dt have. Well, what units would radius have? Radius would have, in this case, centimeters, because that's what the problem is in. And then divided by a unit of time, so divided by minutes. So that's going to be our units for a dr dt that we're going to be looking for. So write an equation to help solve for all these variables. So we're going to write an equation. So in this case, well, what did we have? We knew about dV dt, right? We know about dV dt. That's the basically change of the volume. So let's write an equation for volume. So the volume of a circle, and the volume of a circle is equal to 4/3 pi r cubed. Okay, I'm going to provide a kind of a formula sheet with all these geometry formulas for you guys, but some of them we're going to start to try to memorize. But this is the formula for the volume of a sphere. So now we want to implicitly differentiate both sides with respect to time. So we want to And we did this above, right? But basically we have v equals 4/3 pi r cubed. And we want to do the derivative of both sides. So we want to do d dt and d dt. And I think I have a little bit of lag. Let's see. I don't think it wrote. V equals 4/3 pi r cubed. There we go. So we're going to do d dt to both sides. So we did this earlier, and we get dv dt equals the 3's cancel out, and we get 4 pi r squared dr dt. And so now we're just going to substitute in our variables. So for dv dt, we're going to get negative 230 pi. You can put the units in if you want to put the units in, and the units will all actually cancel out, but I usually don't. I usually just kind of think about my units at the end. Equals 4 pi times, now the r was 4, right? That was the r that they gave us, 4 centimeters, squared, dr dt. And so that's going to give us negative 230 equals, now 4 squared is 16. 16 times another 4 is 64. So 64 pi dr dt. There should have been a pi with the 230. Right, yeah, negative 230 pi. Okay. So the pi's can cancel out. There's a pi on each side. And so we're going to divide by 64. And we get negative 230 over 64. And this is where you want to add your units in, or when you box your answer. Really, if we're going to simplify it, we can simplify it. So dr dt. So we can simplify this, and you can divide both sides by 2. And you can do that a few times, and you'll end up getting negative 46 divided by 13. So, oh no, I messed that up. It is, sorry, you simplify it, and you get negative 115. Yeah, you can only do it once. This is my fault. My notes, I somehow wrote 65 by mistake. Okay, so you divide by 2 once, and you get negative 115 divided by 32. And then that's fully simplified. Now, we do need to add in our units. And so what I was saying is, what are the units for radius? Well, in this case, they're centimeters, because that's what the problem is in. Divided by our units for time would be minutes. So that would be our answer, right? You always need to include units when you have answers for these related rate questions. That basically, the rule of thumb is if the question has units in it, put your answer with units. That's kind of my general rule. Now, if we had put in the units, as we went, and that's something you can do if you're more comfortable with that, right? These units were centimeters cubed per minute, and these units would have been centimeters, but we're going to square them, so they're going to become, basically centimeters squared, and then over here we have centimeters cubed per minute. So what'll happen is a squared will cancel out, and that's why we end up with centimeters per minute. When we divide, the squared will cancel out. But I don't usually do that. I just kind of look at my units at the end. Okay, next. A stone is dropped into a calm body of water, causing ripples in the form of concentric circles. A lot of times I'll draw my picture to kind of help me out. So we have a circle, and we know that circle is going to just be getting bigger and bigger and bigger. Concentric just means it has the same center. You don't really need to know that. Basically, just you can kind of think the ripples in the water, the circles are going to be getting bigger and bigger and bigger. So the radius of the very outer ripple is increasing at 1 foot per second. Okay, so the radius, right? That radius is getting bigger and bigger. Now, keyword is going to be increasing. So increasing is going to be our big keyword here. Increasing is very much like changing. And then rate is another keyword to look out for. Okay, and then as well, what kind of goes with that is the per second. So all of those three words, increasing, rate, and per second, basically told us that that's going to be a dr dt. So dr dt, in this case, is going to be 1 foot per second. And then when the radius is 4 feet, so they gave us, at that one moment in time, the radius is 4 feet. We know it's just r and not dr dt because we didn't see any of those keywords and we don't have per time. At what rate is the total area of the disturbed water changing? So we want at what, that's like what we want, at what rate. So we want dA dt. That's what we're trying to find. So that's kind of reading through these is one of the most important things to start learning how to do. And that's what is going to take the most practice. So we have no variables. And then the rate that was given, we already wrote it, so the 1 foot per second. And what do we want to find? Well, we want to find dA dt. So what's an equation? If I'm trying to find dA dt, what's an equation that has that area for a circle? Well, the area of a circle, you should know this from math 2, is pi r squared. So that's our area of a circle. And so now if we're going to do implicit differentiation to both sides, right, we have a equals pi r squared. We're going to take the derivative with respect to time for both sides. Again, I'm getting a lot of lag. Okay, d dt and d dt. So the derivative of the left side of that area is just going to be dA dt, 1 dA dt. And then on the right side, pi is a constant, so it's going to hang out. And when we bring the pi r squared down, we're going to get 2 pi r. But then because r is different than time, we need to do times dr dt. So we get 2 pi r times dr dt. And that's our implicit. So now we're going to just start substituting. So we're trying to solve for dA dt. And that's going to be equal to 2 pi. Now for r, they gave us the radius in the question. And they told us that, when the radius is 4. Right? And again, you could put the units in and put 4 centimeters. That's fine. I usually don't. And then they also gave us the time. And the time was that 1 foot per second. And again, I'm not going to put in, the units. And I like to just, think of them at the end. So 2 times 4 is 8. And then we have 8 pi. And now this is when I go and I say, okay, this is my answer. What are the units? So what are the units for area? Area, we said earlier, was always units squared. Well, what units did this question have? It had feet, right? So this is going to be 8 pi feet squared. But then per, because of the time, in this question, the time was in seconds. So feet squared per second. And those will be our units. Now, if you wanted to write them in with the 4, you'd have feet per second times, 4 was feet and 1 feet per second. Feet times feet give feet squared. And so that's how that works. So last one for today. Oh no, I think this one I've set for tomorrow. So that's it for today. So I know there's a kind of weird. I don't, when I'm solving these on my own, obviously you're not going to have a box like this. So I do want to just kind of quickly show how I do these so that when you guys are doing the homeworks, it'll make it a little bit easier on you, and how I set up my page. So if I was doing this problem on a homework, right, you don't have that table and you're not going to want to try to memorize something like that table. So kind of what I do is I just, as soon as I realize it's a related rate question, I kind of just, on my page, just break it up into three sections. And so what I always do is on my left section, I put in all of my variables over here, all of like my givens, anything that I'm given in the question. Then in my middle section, I'm going to put any original formulas. And then on my right section, I put basically the derivative rate formulas. And so the way that would kind of look, this is how I would solve that question if it was given on a test, is that I would read through my question. And as I'm reading through my question, we saw that we were given dr dt equals 1. And we were given radius equals 4. If you want to put in the units, that's great too. It'll help you out. So then the original formula, well, and maybe even, what do we want? We want dA dt because that's going to help us, to figure out what we're going to put in the next area. So then what are my original formulas? Well, what formula do I know about for a circle that has area in it? So the formula for a circle for area is pi r squared. So that's what I'm going to put here. And on tomorrow's lesson, you're actually going to have to solve some things in this box And you may have to solve for the area or solve for something. But for today, we don't have to do that. And then in the right box, or the right side, we're going to take the derivative of this guy. So the derivative a was dA dt. And then, the pi r squared gave us equals to 2 pi r dr dt. And now once I get a formula over here, this is where I really start plugging in and solving. So dA dt equals, and we had said that the r was 4 and the dr dt was 1. And so we get 8 pi r feet squared per second. And so that's kind of how I would solve these without having that table that I give you, because an AP question is never going to give you a table like that. They're just going to ask you to solve it. So I know these are a little confusing with the word problems, but once we get the hang of them, they won't be too bad.